Hello, class. So we will be doing, this should be the last of the recorded lectures for chapter 5. And what we're going to do is walk through another problem where this one actually is a polynomial that has complex zeros and show you how to do the calculation. And what would be nice is this would be a really good review of the previous sections as well. So we'll walk through some of those calculations with this equation. So let me just get the whiteboard back up here and we'll walk through this calculation. So this one is f of x equals x cubed minus x squared plus 25x minus 26. So you can see we've been doing a lot of x cubed. X to the fourth, x to the fifth, they're the same process, just a little bit longer. And so you'll see that when you get to the quizzes and exams I give you, they're typically x cubes. So what do we know about this? Well, we know that the y-intercept is 0 minus 26. We know the degree is 3. The maximum number of turning points is 2. 3 minus 1 is 2. What else do we know? So what happens is x goes to positive infinity. Well, again, this is x cubed, so the leading term would be, so that goes to positive infinity. What happens is x goes to negative infinity. And so that would be minus infinity cubed. And there's 3 minuses, so that's minus infinity. So y goes to minus infinity. So what else do we know? Well, here's where it starts to get a little bit more complicated. So what are the x-intercepts? Well, before we do the rational zero theorem, let's do Descartes' theorem one more time, because it'll be useful. Because what do we have? We have an odd degree. And so we know we have to have at least one real zero. And the key is to find that one first and then see what's left. And so Descartes' theorem will help us with the positive and negative real. So if we look at this, we have x cubed minus 8x squared plus 25x minus 26. So this one has one change, 2 changes, and that's the maximum you could have, right? 3. So we'd have 3. 3 minus 2 is 1. So for positive, there's either a 3 or a 1. So let's see what happens in the negative one. So you have to do the transformation. So that would be minus x cubed minus x times minus x squared plus 25 times minus x minus 26. So we have 3 negatives there. We have 3 negatives here, 2 and 3. We have 1 negative here, and we have the constant never changes. But what's cool about this is look what happens. No changes, right? So there is 0 negative. So we know that the real 0 has to be positive. That's very helpful. So let's do our little table again. And since we only have 2 columns, right? Which is nice. And they both add up to 3. So that would be positive, negative, and complex. And so here would be 3 or 1. There's no negatives. And so when we add this up, this would be a 0 here and a 2 here. So we only have 2 possibilities. There's 1 real positive and 2 complex, which is the case here, since I want to show you how to calculate complex. Or you could have all 3 positive reals. So the next step is to do the rational zero theorem, because this will give us the possibilities And then using Descartes' theorem, we could eliminate some of them because we have no negatives. So that combination usually is very powerful. So again, we have minus 26. So that'd be plus or minus 26 and plus or minus 1. And then plus or minus 2 and plus or minus 13. And we divide all that by plus or minus 1, which is nice. And so you could see that these are our possibilities. And then you say to yourself, from Descartes' theorem, I can get rid of all the negatives. So I erase those. And now we're only down to 4 possibilities. So let's try them. And so I always start with the easiest one first, see what we get. So 1 cubed minus 8 cubed plus 25 times 1 minus 26. So what do we have? 1 minus 8 plus 25 minus 26, and that's minus 8. Is that a 0? Nope. This has to equal 0 or it doesn't work. So let's try 2. So when you do 2, you get 2 cubed minus 8 times 2 squared. 25 times 2 minus 26. So when you do that, you would get 8 minus 32 plus 50 minus 26, and that would be 58 minus 58, and that's 0, and so we find the positive 0. And you'll see in this class, it's going to end up being a rational number. Just makes the calculations doable. And so, all right, so what is our factor? Our factor is x minus 2, right? And so now what do we need to do? We need to simplify this, and the only way to do that is with our division to find the quadratic factor. And so we do that. I will do the synthetic division again. And so a little bit of erasing here. So when we do the synthetic division, it would be a 2 over here. And again, that's cubed, squared, and constant. So that would be 1 minus 8, 25, and minus 26. So you bring down the 1. 1 times 2 is 2. That would be minus 6. So minus 6 times 2 is minus 12. That would be 13. 13 times 2 is 26. And you better get 0 or we did something wrong. So what are we left with? X squared minus 6x plus 13. We have x minus 2. Well, 13 is a prime number. And so if you try to factor that, 13 times 1 minus 13 times minus 1 doesn't, when you add up, does not equal 6. So you say to yourself, factoring is not doable. And so what should we do? Well, let's do the quadratic formula. So when you do the quadratic formula, it would be the a value is 1, the b value is minus 6, and the c value is plus 13. So it's minus b, so that would be minus a minus 6, plus or minus the square root of b squared, which is minus 6 squared, minus 4 times a times c, all over 2a, which is 2 times 1. So minus a minus 6 is a plus 6 here. So I'm just going to do a little bit of erasing because I'm running out of room. So this would be plus 6. So the key is what's underneath the radical. So this would be 6 times 6, which is 36, minus 4 times 13 is minus 52. So if you do that subtraction, you would get minus 16. And you say, okay, again, just using an eraser because I'm running out of space. What ends up here is minus 16. And what's the square root of minus 16? Well, the square root of 16 is 4. And what's the square root of minus 1? I. And so that's what ends up happening is this gets simplified to plus or minus 4i. And so we have, just make that line a little bit shorter now. And now we have two solutions, right? 6 plus 4i divided by 2. And that would be 3 plus 2i. And then 6 minus 4i divided by 2. And that would be 3 minus 2i. They better be complex conjugates of each other, right? And they are. And so how do we rewrite this in factored form? Well, now we had the first real of 0, which is x equals 2. And then this would be x minus 3 minus 2i. And then x minus 3 plus 2i. So I do want to point out that I'm not sure how my math lab will want you to enter these, but sometimes they'll want you to enter these without all those parentheses, just in case. Let me show you how to do that. On a quiz or an exam, you could leave it just like that. But here would be x minus 2, right? And then basically we're going to distribute the minus in there. So that would be x minus 3, and that would be plus 2i. And that would be x minus 3 minus 2i. They might ask you to write it that way. So how would you sketch this like we did before? Well, we have only one real 0, and that occurs at x equals 2, right? And then we have this y-intercept is at 0 minus 26, which is way down there. And then what do we have? Well, we have the leading term or end behavior that looks as x goes to positive infinity, y goes to positive infinity, and as x goes to negative infinity, like y goes to negative infinity. So somehow the graph has to come over here, come up here, and connect that way. Remember, the multiplicity is odd, so it crosses at that particular point. So I paused this for a second so I could type the equation in on Desmos and kind of show you what it would look like. And you could see that this is their equation. And when you type it in, you see that at minus infinity, it goes to x equals minus infinity, but y goes to minus infinity. You could see that if we zoom in over here, it crosses right at minus 26 for y, x equals 0. And we continue to go up, and what ends up happening is we cross the x-axis at our one real 0 at x equals 2. And then it shoots back up to infinity as x goes to positive infinity. So I think that's finally done, right? So that ends chapter 5. And that was an example of calculation of complex zeros.